Right now, on Easter Island, a 435-ton stone statue is standing upright. And according to a groundbreaking 2025 study using physics, 3D modeling, and a full-scale replica, it didn't get there by being dragged, rolled on logs, or hauled on a flat sled. It walked there, upright, rocked gently side to side by a small team of people pulling ropes. It stepped across the landscape like an impossibly heavy toddler being coaxed across a room, refusing to fall even once during its entire journey. This is one of the most quietly mind-blowing facts in all of archaeology, and it opens the door to a much bigger question. How did ancient humans, across completely unrelated cultures separated by oceans and thousands of years, manage to build some of the heaviest, most precisely engineered structures on the planet using nothing but rope, wood, stone, water, and sheer human effort? There were no cranes, no trucks, and no electricity. Just people, physics they understood intuitively without ever writing down a single equation, and problems so enormous that solving them required entire societies to organize around a single shared goal for decades. To understand how they did it, we have to look at three incredible stories: a trick with wet sand that quietly defeated friction, a French architect who quit his job to solve a 4,000-year-old mystery with a laptop, and a statue that literally walked under its own carefully engineered momentum. Let's start with the most famous construction project in human history, which sets the bar for everything else: the Great Pyramid of Giza. The numbers alone are dizzying. The Great Pyramid contains more than 3 million individual stone blocks, each weighing anywhere from 3 to 90 tons. They were stacked with a level of precision that still humbles modern engineers, all without iron tools, heavy lifting machinery, or even the common use of the wheel. Yet 4,500 years later, it's still standing, having survived wars, earthquakes, and the grinding passage of time far better than most modern buildings. But first, we have to bust a massive myth. The pyramid was not built by millions of enslaved laborers toiling under a whip. Archaeological evidence, including detailed logbooks of 40-man work crews, tells a very different story. The project actually relied on a highly organized workforce of about 4,000 primary laborers, the skilled quarry workers and masons, supported by another 16,000 to 20,000 secondary workers who built ramps, manufactured tools, and kept the entire operation clothed and fed. This wasn't a brutal slave camp. It was a masterclass in logistics, directed by careful record-keeping on papyrus and a highly efficient chain of command. So how did they actually lift blocks weighing as much as several modern cars? For decades, the dominant theory was that the builders used a single, massive straight ramp running up the side of the pyramid. But modern researchers have largely discredited this. Building a ramp long and stable enough to reach the pyramid's peak would have required more raw material and labor than the pyramid itself, and no archaeological trace of such a massive structure has ever been found. In 1999, a French architect named Jean-Pierre Houdin did something obsessive. He quit his comfortable job to solve this riddle. Using detailed computer-aided design modeling and sheer persistence, Houdin proposed the internal ramp theory. His model suggests the builders used a conventional external ramp for the first 30% of the pyramid's height, and then switched to a spiraling ramp built directly into the interior of the structure. Workers hauled the stones up a corridor that wound continuously around the pyramid's solid core. This elegant theory explains the total absence of physical evidence for a massive external ramp, because once the pyramid was finished, the stones from the lower external ramp were simply recycled and built directly into the pyramid's upper levels. But the ingenious engineering didn't stop there. A 2012 papyrus discovery revealed that the Egyptians used now-vanished branches of the Nile River to transport massive stone blocks incredibly close to the construction site, letting the water carry the bulk of the weight before human muscle ever took over. And then there is the secret weapon of the desert: wet sand. Ancient Egyptian wall paintings clearly depict workers pouring water directly in front of the sledges used to drag these massive stones. For a long time, historians assumed this was a ceremonial gesture. It wasn't. Wetting dry sand just enough creates a thin, stabilizing film of water tension between the individual grains. This dramatically reduces friction, cutting the required pulling force by roughly half. The ancient Egyptians had figured out a genuine principle of granular physics through trial and observation that modern scientists wouldn't formally measure and explain for another 4,000 years. Now let's cross an entire ocean and travel forward in time to a windswept plain in southern England, where Stonehenge presents a different flavor of the exact same engineering problem. Erected around 2500 BC, Stonehenge consists of massive stones, some weighing up to 30 tons, arranged in a precise circle. But the truly baffling part of Stonehenge isn't how they assembled it once the stones arrived, it's the journey they took to get there. Some of the monuments, bluestones, originated in the Preseli Hills of Wales, nearly 200 miles away. How do you move 30-ton stones across 200 miles of hilly, ancient terrain with no wheeled vehicles and no draft animals? The leading theory is a hybrid transport system. Workers used sledges and rollers made of tree trunks to drag the stones overland, then transferred them onto rafts once they reached a navigable river or the coastline, letting the water carry the weight. Once on site, raising these massive pillars into an upright position didn't require raw brute force. Instead, they used counterweights and patient leverage, slowly rocking each pillar from a horizontal resting position to a vertical one, inch by careful inch. They bypassed gravity not by fighting it head-on, but by breaking one impossible lift into a long, highly controlled sequence of small, manageable steps. Which brings us back to Easter Island, and perhaps the most satisfying solved mystery in ancient engineering, because the actual answer was hiding in plain sight within local oral tradition the entire time. For generations, academic researchers debated how the Rapa Nui people moved their massive Moai statues, some weighing more than 80 tons, from the quarry to ceremonial platforms across the island. The leading academic theories all assumed the statues were dragged flat on wooden sledges or rolled on logs. But there was a glaring problem. Archaeological surveys of the ancient roads consistently found no trackways, no roller depressions, and no sledge marks. Meanwhile, Rapa Nui oral tradition had been insisting on something else entirely. The statues simply walked to their destinations. A 2025 study led by anthropologists Carl Lipo and Terry Hunt decided to take that oral tradition seriously. By combining physics modeling, 3D scanning, and hands-on field experiments, they found startlingly strong support for what the islanders had been saying all along. Analyzing nearly 1,000 Moai statues, including 62 found abandoned along the ancient transport roads, the research team discovered that successfully transported statues shared a very specific set of design features. A wide, D-shaped base and a deliberate forward lean of 5 to 15 degrees. This wasn't an artistic choice. It was functional engineering built directly into the statue's shape. With sturdy ropes attached to either side of an upright Moai, a coordinated team could pull from alternating sides. Because of that deliberate forward lean and rounded front base, the side-to-side rocking motion caused the statue to pivot and take a small, controlled step forward. It is the exact same physics you use to move a heavy refrigerator across a kitchen floor by rocking it from corner to corner rather than trying to drag it flat. To prove it, the research team built a full-scale, 35-ton replica Moai with the correct forward-leaning design and successfully walked it 100 meters in about 40 minutes using only 18 people. Once the rocking motion was established, pendulum dynamics took over, and each step actually became progressively easier to sustain. An average-sized Moai could realistically walk roughly 1,000 feet per hour. Even the ancient roads were purpose-built for this. They measured around 4–5 meters wide and were gently concave, a shape that would make dragging a flat statue incredibly difficult, but perfectly stabilized and upright, walking one. And the statues that never made it, the ones found abandoned along the roads, weren't evidence against the walking theory. They actually confirmed it. Roughly half of these broken statues were found within just 2 kilometers of the quarry, with the frequency of abandonment steadily decreasing the farther they traveled. They represent occasional mechanical failures during the difficult, early stages of transport, left exactly where they fell. What ties the pyramids, Stonehenge, and the Moai together is a shared human brilliance. None of these societies had heavy machinery, iron tools, or the wheel. Yet entirely independently, they all arrived at the exact same set of physical principles. Reduce friction wherever possible, whether through wetted sand, wooden rollers, or concave roads. Convert one overwhelming task into a sequence of small, manageable steps.